Hi everyone and welcome to another lecture. In the past lecture we gave a schematic information how we can deal with the infinite dimension. That is, our vector space is now infinite dimensional, and in this lecture we are going to see more details about it. So if you recall that we started talking about functions and we said that this function contains some information, and let's say you want to transfer this information to a distant place and you are not allowed for a continuous transmission of the information. You can discretize it and then you can send it, and the other person that is receiving the function information can reconstruct the whole thing by using that information. So let us be more abstract today, and what we're going to do is that we're going to say that we can take this function. Let's say this is the graph of this function, and we can denote the discrete approximation to this function that coincides with it at n points and vanishes in between. And we can do that by using something following. Let's say the information can be discretized, or let's say some discrete parts, and let's say they form a set or a collection of objects. So let's not use the set. Instead we are going to stick with the terminology that some collection of information, let's say f of n of x1. This n means that I have divided this function's information into n subintervals, like say this is 1, this is 2, this is 3, this is n. There is more lines like this in between. So this is f of n x1, that is the information of the function at x equals to 1. Don't confuse this thing with the number that is over here. And then f of n x2, f of n x3, up to f of n xn. Alright, so since these are discretized, what we can do now is that we can interpret this ordered tuple. So this is an ordered tuple. Now what we can do is that we are going to interpret this ordered tuple in a ket. So let's do that. We are going to do that by using a ket f of n, and here I can place all of these ordered tuples. That is f of n x1, f of n x2, f of n xn. And using this ordered tuple, you can see that the familiar structure for finite dimensional vector spaces will arise, because this can be written as f of n x1 times 1, 0, 0, 0. Then you can go for f of n x2. Okay, this doesn't look like n, so yeah, x2, 0, 1, 0, 0, 0, 0 all the way. And similarly for f of n xn, this can be written as 0, 0, all the way, and the last element is just 1. So this is familiar from our discussion on the finite dimensional vector space, right? And here, if you can recall the discussion on finite dimensional vector spaces, we could write it as f of n x1, 1, f of n x2, that is at x2, 2, and so on. And this 1s, 2, 3, these kets will be my basis. Now these are my basis vectors. This is also a basis vector, and so on. And this is a finite dimensional vector space. But to get the function accurately, as from this graph, as you can see, we have to extend n, that is when n goes to infinity. and all the widths, that is all the lines that you are drawing. If you draw a line like this in the black line and another red line, their distance should be as small as possible. So the distance between them should go to 0. That is, we are talking about the limit del x goes to 0, because if this red point is denoted as x of, let's say, 0, this black point is representing x of 0.0 plus some delta x, then this delta x should go to 0, and that would mean our n should go to infinity, just like you do in calculus. So since we are dealing with some x1, x2 and x3, it's rather a convention. It's not absolutely mandatory, but it's a convention to write these ones as x1, because the information that is carrying is this coefficient, right? This coefficient is our information, and that is associated with our point x1. So that's why people write it as x1. Also, it helps us to distinguish between that whether we are dealing with a finite dimensional space or an infinite dimensional space. And this whole thing will also help us in future lectures to representing a function in the coordinate basis, and you will see that as we go along. So if you just follow this convention, instead of 1 you are replacing with x1, so this will be f of n x2, and this will be x2, so on, dot 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 dot, plus f of n that carries the information of x of n, and this is our basis vector. So from here, that is from this part of the calculation where we represented our basis like we used to do in finite dimensional space, you can see that since these are bases, we can say xi xj will be delta ij, right? And this reminds us of the fact that basis vectors are orthogonal. So this is a orthogonality property. And also the completeness relation that we saw for finite dimensional space, since at first we are cutting the function into n subintervals, like you can see in this graph, our completeness relation will be this. This is the identity matrix, n cross n identity matrix, and we want to see what will happen when n goes to infinity. So let me just write it down. We want to see what will happen when n goes to infinity, and this will be our infinite dimensional case. So if you try to imagine a space containing n mutually perpendicular axes, that is these vectors over here, that is the bases, and they will represent one for each point xi for the function, that is some information that is carried along with this point. For example, here f of n x1 is just saying that you have divided the function into n intervals, and this x1 means you are evaluating the function at point x1, and that is associated with this basis vector we are calling x1, right? And this looks like a projection itself, because if you recall from finite dimensional spaces that if you had a vector like this v, if you use the Kate notation, or let me just get rid of the Kate notation because I want to make it more familiar. For example, if you had a vector like this was also discussed in the finite dimensional spaces, then you can easily tell that on the x-axis the projection of vector along the x-axis was 2. On the y-axis the projection of this vector v was just 3. Similarly, the projection of the function at point x1 is just f of x1. The projection at point x2 is just f of x2, and so on. And to construct the whole function we need all of the points. So that's like an infinite amount of points from our interval. If you just recall that we took the interval, let's say, from 0 to L. It was a closed interval. Yeah. So that's why we are saying that these are our projections, that is the coefficients themselves. So now let's write this whole thing in a more compact notation. That is, this get f of n will represent the function, or the function that we are treating as a vector, that is divided into n intervals or sub intervals, whatever you want to call them, between 0 to L, and they can be represented via an expansion. And let's write our expansion as this, since we are considering n sub intervals. So this is f of x1, sorry, f of xi, and this is just mimicking the fact that we wrote f of n as this, right? Okay, so far so good. Next, let's say we want to work like this, and let's take another function g of n, which is similar to this. That is, we take another function and we cut it into n pieces, and we want to see the inner product. We want to see, sorry, the inner product of f of n, g of n. So far we are also considering that these functions are real valued. So let's write it down that we are assuming f and g are real valued functions. And we'll take the general case a bit later. So if you just write this whole thing down, there will be two summation indices that will vary up to n, I and j, and since f and j can be written like this, we can have f of n with a star over here. That means a complex conjugation, but since they are real valued, we can just get rid of the star, and then you will have this g of n thing, right? And obviously both of them will carry some x's, but I'm not writing them explicitly. And g of x can be written in this xi basis. So since we are adopting the general case, let's just write x of j, and this will be x of y. And these are basis vectors, right? And they are orthogonal to each other, so they will give us a delta ij. And if you sum over this ij now like this, that is f of n x of I, g of n x of j, and there is delta ij, you get rid of the summations. That is, you sum over one of the indices. Let's sum over this j, and we'll have I equals to 1 to n. Obviously you can write 1 over here if you want, but it doesn't matter. So finally you will have f of n xi, gn xi, right? Similar to our finite dimensional cases. And now what we want to do, we want to go to infinite dimensional space. So now we ask, what happens to this inner product? Happens to this inner product that is represented with fn gn when n goes to infinity. Now this sum will diverge. You can see that even when our basis vectors are infinite, we don't have any problem with the vector addition and scalar multiplication, because they're not diverging or all that. But this inner product thing, this will diverge. So a natural choice that will give us a smooth inner product, that is, when the limit n goes to infinity, we can obtain a smooth, how do you say this, a smooth result or a smooth limit when n goes to infinity, is to replace this inner product. So let me just write, by replacing, or let's say a new definition for inner product when n goes to infinity would be f of n, g of n. We keep in the back of our head that this n is going to infinity, and this will be replaced with I equals to 1 to n. You will have f of n xi, g of n xi. But now what you want to do, you want to introduce something delta, and this delta is given by, recall that our interval was something like this, 0 to L. So the difference between these interval points, that is L minus 0, the highest point minus the lowest point. So this is the interval divided by n plus 1. Why n plus 1? Because we divided the interval into n segments, right? So there will be n plus 1 pieces of information, or let's say partitions, not information, sorry. You should rather call it n plus 1 partitions. And as n goes to infinity, this delta goes to 0. So you can see it schematically from here. So as n goes to infinity, delta goes to 0. And if you recall from calculus that whenever you had a sum and you had something a delta like this over here, this sum was replaced by an integral, right? Because if you consider two bars, let's say this is 1x1, this is the x2, and this is delta. As delta approaches 0, the sum gets replaced by the integral. So finally, so let me write finally, when n goes to infinity, the sum will be replaced by the integral. Obviously this integral will be a definite integral, so let me just write that down, and that will depend on the functions over the interval on which the function is defined on, and we defined our functions on this interval 0 to L. So this inner product will now be written as f and g, and notice that I am getting rid of this n right now, because I told you before that if you want to have the full information of function f and function g, what you need to do is you need to take n goes to infinity, because for example, let's say there are 2 points between 0 to L as x1 and x2, right? And in between them there are also infinitely many points. So that's why to get the full information, you need to increase your partitions. That means you need to increase your n. So that's why I'm taking this limit n goes to infinity. And finally, if you replace this delta with an dx and this sum over here with an integral, this will look like 0 to L. You will have f of x, g of x. Also recall that this f and g are real valued function, and there will be a dx. So this is our generalization of the inner product for the real valued function. So let me write it down. Generalization of inner product in infinite dimension for real valued function. Now what if both of them are complex valued? So what if f of x and g of x are complex valued / complex functions, that is, they contain some complex parameters? The idea for them will be the same as real valued functions, but now if you have complex valued functions, you will have this integral over here just like before, and instead of f, now you will have f star, that is the complex conjugate of this function, and g of x, then you will have dx. And this is the most general inner product that you can have in function spaces. For example, if you have a function called f of x as e to the power I kx, then f of star of x will be just e to the power minus I kx. Just take the complex conjugate of it. And if you draw an analogy with the finite dimensional case, that two vectors were orthogonal when the inner product was 0. So if you have two functions, if you have something like this would mean f of x and g of x are orthogonal to each other within that interval. You can take an example, for example, sine and the cosine, and if you just integrate from, if I'm not wrong, it's 0 to pi, then all of this will vanish. Or instead of 0 to pi, let's just say minus pi to pi. If you take minus pi to pi like this, pi to minus pi, and have sine x, cosine x, dx, this will be 0. So within this interval, they are orthogonal to each other. And in the bracket notation, you can write it like this: sine x, cosine x, and there's 0. So they are orthogonal to each other. And if you recall that bases are orthogonal to each other as well. So from here, you can see that the sine and cosines with up to some interval, they are orthogonal to each other, and they sometimes form a basis for expansion of functions. And from here, the idea of Fourier transformation also emerges, but that is something we are not going to discuss. But the main idea is to keep this thing in mind, that how we generalized the inner product for the infinite dimensional spaces. So we took care of the inner product thing. The next thing we are going to look at is the completeness relation. So when our dimension was finite, let's say in dimensional space, we wrote it like this, right? The identity matrix. And here, similarly, when you take n goes to infinity and you put a delta over here, those are the things you need to do. And this gets replaced by an integral, and this will just be, instead of xi, you take all the points, and dx, you just call it 1. You can obviously write it like this identity operation as well if you want, but this is our completeness relation in the infinite dimension. And this will be pretty useful as we go along, and we'll see that how they're useful. And the final thing that we want to see for today is that what is the function itself, because we are denoting the function like this, an abstract ket vector, right? But we also said before that the function, when it's projected onto the x basis, that is the coordinate basis that you are familiar with, they have coefficients like this: f of x1, f of x2. That is, if the function is evaluated at x1, x2, and so on. So to get the full function, what we need to do is to take this abstract function. It's not a function, to be honest. It's a way to represent the function as an abstract ket object, an abstract vector. And from this vector space, if you just take an inner product in the coordinate basis, you will get your function, f of x. This is on the coordinate basis representation. Coordinate basis representation. Okay. In quantum mechanics, we can also take the function that is the abstract function over here and project it into the momentum basis, that is denoted by p, and this will be then f of p. So this is on the momentum basis. So this is the power of abstraction, that you are dealing with something in general, but then you can always take the representations that is convenient for you. And in fact, these two are related via some Fourier transformation. For example, if you take this f of x and you want to write it in terms of f of p, all you need to do is that there is something called a Fourier transformation. I am not showing you the integral, the Fourier integral, but this Fourier transformation, denoting it by some curly f, this will act on it. it will kill all the p's. That means it will integrate over all the p's, and it will only left x, and the whole thing will turn into a function of x. So this will be it for today. I hope you understood that how to start from scratch, that is the finite dimensional space, and we go to the infinite dimensional space. And in the next lecture we are going to talk about a peculiar function, which is not a function at all, rather called a distribution. Distribution that is known as the Dirac delta distribution, and that will be pretty helpful for us that when we want to calculate all these stuffs, because you can see that if I take these inner products like this, when they're orthogonal to each other, I'm saying they're 0, and when they're not, I'm not saying anything, and that should just give me a norm of the whole thing, right? So to do it in a more general sense, we'll need that delta function, and in the next lecture we're going to see it. So this will be it for today, and thank you.